Hi friends, my dear students, and 12th Physics and second volume, unit number, at present it may be called as ninth unit, but as per in textbook 84.6 binding energy of curve, binding energy curve. So it's a very important curve to explain the binding energy, binding energy per nucleon, binding energy per nucleon, and that's why the curve shows in the figure that how to draw the figure and what are the results that we are attaining there from this curve. That's we are going to see today. Before going to see this curve, already last class we have seen the binding energy. It is nothing but ZMH, that is called mass of hydrogen, that is called Z, plus mass of neutron Nmn minus atomic mass into c square. That is a binding energy. When you say this is called binding energy. If you are say binding energy bar, it is nothing but the binding energy per nucleon. Binding energy per nucleon. Then it may called as B bar. That is that binding energy divided by atomic mass number. Atomic mass number. That means B bar is nothing but binding energy per nucleon. Here the total number of nucleon is said to be A. Then if you are dividing this binding energy by A, then binding energy for nucleon B bar. So now we have to draw the graph between B bar in million electron volt in the y-axis, and you have to consider the number of nucleons in the x-axis, A, mass number. Now, before going to start, what is meant by binding energy per nucleon? Binding energy per nucleon is nothing but the energy required to separate single nucleon, the energy required to the single nucleon to bring out the nucleon from the nucleus, that is called binding energy bar, binding energy bar. The average binding energy bar uniform, the average binding energy per nucleon is the energy required to separate single nucleon from the particular nucleus. That's the definition of the binding energy. Now, when we think about the graph, we are bifurcated in the x-axis 0, 50, 100, 150, 200 and 250. Whereas in the y-axis you have to consider million electron volt binding energy per nucleon. The amount required to separate the nucleons from the nucleus, that is called the binding energy per nucleon. Here you have to consider 2, 4, 6, 8, 10. Up to the maximum value, this is the maximum value attaining here in graph as we see. That is called 8.8, 8.8, that is 8.8 million electron volt. When A equal to 56, A equal to 56. So this is the state we have to explain next. Before we have to start from 1H1, 1H2, then 2He3. This is the isotope of hydrogen, this is the isotope of helium. Then the curve started straight away rising to the 7, that is helium isotopes 2He4, 2He4 helium, again come back to the 4 million electron volt, again rises to 7.8, then again decreases, again increases, again decreases, then it may reach the peak value of 8.8 million electron volt when A equal when A equal when A equal to 56, then the BE bar is equal to 8.8 million electron volt. This is for ferric. This is for ferric. Ferric 2656. This means this shows that here in less than 50 or less than 40, less than 40, this is the smallest mass number. Smallest mass number. It is here. Now we are going to explain 40 in between 140. 40 to 120 or 140. This is the one stage. Less than 40. This is the another stage. This is the first, second, third. The first one indicates that the atomic number A is equal to 40. A is equal to 40 and A is equal to 140. A is equal to 140. Or for simplification, we have to consider this is called 120. You have to consider 120. Now, because stands same 50, 120, that's why I have to consider this value of 120 like this. Now, part 1 is a very important role. That is, in between 40 to 120, it is a stable non-radiating substances. Non-radiating substances. It explains that what is the meaning of ferric 2656. It attained the maximum value of 8.8 million electron volt, which one is the highest binding energy per nucleon in the 8.8 million electron volt. This one is very stronger. You cannot be able to easily break out or fission process which will not take place easily. So that when we study about when A is equal to 40, A is equal to 40 and A is equal to 120, within this state, within this atomic mass number, the binding energy, average binding energy per nucleon, that is equal to 8.5 million electron volt. This is average. 8.5 million electron volt. In this stage, these are all constant. This is very strongest bonding and non-radiating substances. It shows that non-radiating substances when A equal to 40 and A equal to 120. These elements comparatively more binding energy per nucleon than any other elements when A is equal to 40 and A is equal to 120. So, on because of this higher value, then it is the most stable element. When A is greater than or less than 120, the elements which are lying in this category are most stable. are more stable and non-radioactive substances. Stable, stable and non-radioactive substances. Non-radioactive, radioactive substances. Non-radioactive elements. This is the very important points. Then the first point is clear for ferric 8.8 million electron volt rapidly, not rapidly, slowly it will be raised. At last it reaches the maximum value for ferric element of iron. That's the maximum binding energy of nucleon, which is the very strongest element. That is why 8.8 million electron volt. When we consider about the atomic mass number lying 40 to 120, 40 to 120, then this stage is more stable as well as non-radioactive substances. Non-radioactive substances. And furthermore, if you are increasing atomic mass number, the binding energy which will be slowly decreases until 7.6 or nearly about 7.6 million electron volt. 7.6 million electron volt for uranium or heaviest nucleus. Atomic mass number is heavy, that is 238, nearly about 238. 238. That's why this this dot of uranium 92 uranium 238 indicates that mass number is heavy but not a stable one. Easily it can be breakable. Easily we can break it out. Whether fission process may happen easily for uranium. When you hit the uranium by means of any neutron or any other accelerated particle, the uranium may be split into two or more pieces. That's why it is not a stable one. It is easily breakable. That's a very important concept of second and third. Then fourth one is fourth one is very important. When if you consider the lowest of A is equal to 28 or less than 28 and less than 56, that is the small atomic mass number element. Let us consider smallest atomic mass number 1, another one, then here both are fused together. Both are fused together and form a new nucleus. That's a listen here constantly. Very important concept. Here this is less than 28. Here this one is less than 28. Another one is less than 56. Both are combined together, fused together. Fusion process. Not fission process, fusion process. Fusion process may happen, then new form of nucleus which are formed. Here new form of nucleus binding energy per nucleon is higher than the value of the prior one. So that along with this nucleus there may be enormous radiation which are outcoming during this process. That's a very important. We already seen in the last class, if you are calculate the binding energy of this separation is higher than the total, but here the higher value may be radiated by means of radiation. That is why we get more number of radiation, more number of energy that was emitted during the process of fusion process Along with the new form of nucleus, there may be enormous energy radiations may occur in the process of smallest nucleus fuse together and form another nucleus. That's very important. The same this is happening. This is a very good example for a nuclear fusion process, and this was followed by the hydrogen atom bomb. Hydrogen atom bomb. This is the basic principle how we are exploring the hydrogen atom bomb. Fusion process fusion process is the main causes to create the hydrogen bomb. So when you blast the bomb, then enormous energy which will be happened. That's why fusion is very dangerous than the fission process. Fission process. When compared to the fission process, the less energy comparatively fusion process. That's why hydrogen bomb is most dangerous weapon than another atom bomb. Atom bomb. When you say fission, then there may be an atom bomb. Atom bomb, not hydrogen bomb. When you say fusion, there may be an atom bomb. So here the energy released during the process of the fusion higher than the energy released in the atom bomb. Higher than the energy released in the atom bomb. That's a very good important concept that you have to understand here. In the World War First and World War Second, we are utilizing only atom bomb, not hydrogen bomb. If suppose the chain reaction may happen in the open way, he could not be able to stop. In Japan, Hiroshima, Nagasaki, that was happened only because of the atom bomb, not the hydrogen bomb. Still now the radiation may be radiated. Still now we are able to receive the radiation, amount of radiation less amount of radiation in Japan, Hiroshima and Nagasaki. That's why uncontrolled chain reaction that was happened in the fission process. You suppose if you are happening when you are putting the nuclear bomb of hydrogen bomb uncontrolled manner, then there is not even a single uh, alive things which is possible in the earth. Such imagination, you have to think about the how much of energy which was produced in the fusion process than the fission process. Fission process. Are you clear? Fusion. Here A is called one nucleus, smallest less than 28, and another one is the smallest nucleus, B is less than 58. Both are fused together and form C nucleus. Here the binding energy of the C is heavier than the prior one, A and B. That's why the remaining amount of mass which will be radiated by means of energy, that's the thing that you have to understand clearly here. Then at last we have to consider a very important concept of atomic heavier. When you are thinking about uranium 9238 splitted into three or two atoms like here along with the neutrons, then there may be a radiation, then there may be emission of radiation. This energy radiation is lesser than the energy radiation of the nuclear fusion process. That's a very important concept. Fusion is more dangerous than the fission process. The energy released in the fusion is much more greater than the energy released in the fission process. For heaviest nucleus, fission may take place. For the lowest A less than 56 or less than 28 fused together, then this fission may be taking place. That's a very important explanation by means of this curvature. B binding energy of nucleon and atomic mass number. This is very important 5 mark question. Generally, it may be asked in your examination. If you have any doubt, then ask any questions. Give the comment. I will explain in detailed manner. Okay. Thank you, my friends. Subscribe my channel and refer your friends and click all bells to watch my video continuously. Thank you.